So, 4a, compare without calculation the scattering by nuclei of alpha particles and high energy electrons. Alright, so what we're considering then is two basic scenarios. We've got our material with, assume, just one row of atoms, and we could be firing a high energy electron at it. Or we could be, when we're comparing that to the same material, but what we're going to be doing then is firing an alpha particle at it. Now obviously the alpha particle is positive and all these nuclei themselves are positive. So we're going to compare them. So both the electron, high energy electron, and the alpha particle are deflected by the electrostatic force. Now the effect on them is slightly different. So the alpha particle is repelled by the, and I should say, so if I put positive, alpha particle is repelled by the positive nucleus. So that will deflecting the alpha particles away from the nucleus. So I'll deflect them away from the nucleus, and it could cause them to deflect by more than 90 degrees, or even, and I'm going to say bounce back. When I say bounce back, obviously they're not hitting the nuclei. The repulsion force is enough that they actually get pushed straight back. Now that's different. The negative electron is attracted to the nucleus. So the negative electron is attracted to the nucleus, deflecting, so that's going to be deflecting the electrons towards the nucleus. So deflecting electrons, I guess ultimately the thing that could happen that's completely different is, rather than actually causing them to bounce back or deflect by more than 90 degrees, it could result in electron capture, and could result in electron capture. So these things are in the opposite directions. One's being attracted, one's being repelled, or the other's being retracted. And one could result in being deflecting by more than 90 degrees and being bounced back, and this one could result in electron capture. Now there's another effect going on. So particles, so the alpha and high energy electron also undergo diffraction, because these nuclei are acting as discrete elements and you've got slots between them for these particles to pass through, so they undergo diffraction. So the alpha particle, de Broglie or de Broglie wavelength, and the separation between nuclei such that there is no, or you could say negligible, diffraction. Okay, so basically their wavelength, if you remember, lambda is equal to h upon p, which is h upon mv, so their mass times by their velocity is such that their wavelength is so different to the separation between these nuclei that you don't see any diffraction. However, the high energy electrons wavelength, and it's their de Broglie wavelength, is comparable to the separation between nuclei, and therefore diffraction is observed. Okay, so from that perspective, what we've got then is two kind of different scenarios. The alpha particle is repelled, the electron is attracted. The alpha wave, nothing happens because its wavelength isn't comparable to the separation. The electron wave undergoes diffraction because its wavelength is comparable to the separation between the nuclei. Hopefully that makes sense. Thank you very much.